Spacecraft propulsion refers to the technology and systems used to generate the thrust needed to propel spacecraft through space. The primary goal of spacecraft propulsion is to overcome the gravitational forces of celestial bodies, achieve orbit, and conduct interplanetary or interstellar missions. Various propulsion systems have been developed to meet the diverse requirements of space exploration, ranging from launching satellites into Earth orbit to sending probes to distant planets and exploring the depths of the cosmos. Key principles and methods of spacecraft propulsion. Rocket engines. Rocket engines are the most common propulsion systems for spacecraft. They operate on the principle of action and reaction, as described by Newton's third law of motion. A rocket expels mass in one direction, generating thrust in the opposite direction. Chemical propulsion. Chemical rockets use chemical reactions to produce high-speed exhaust gases that are expelled to create thrust. The most common propellants in chemical rockets are liquid or solid fuels combined with oxidizers. Liquid rocket engines allow precise control of thrust, while solid rocket motors are simpler and often used in boosters. Electric propulsion. Electric propulsion systems use electric or electromagnetic principles to accelerate ions or other charged particles to produce thrust. Common types of electric propulsion include ion thrusters and Hall effect thrusters. While electric propulsion provides higher efficiency than chemical rockets, it typically generates lower thrust, making it suitable for specific mission profiles such as deep space exploration. Solar sails. Solar sails use the pressure of sunlight to propel spacecraft. Thin, reflective sails capture solar radiation and transfer momentum to the spacecraft, creating a gentle but continuous acceleration. Solar sails are particularly useful for long-duration missions and can operate without the need for propellant. Nuclear propulsion. Nuclear propulsion systems involve the use of nuclear reactions to heat a propellant, which is then expelled to produce thrust. Nuclear thermal propulsion and nuclear electric propulsion are two concepts that have been explored for potential use in future deep space missions. Nuclear thermal propulsion uses a nuclear reactor to heat a propellant, while nuclear electric propulsion generates electricity for ion or plasma thrusters. Photonic propulsion. Photonic or laser propulsion relies on directed beams of light to propel spacecraft. This concept includes laser propulsion, where ground-based lasers or orbital laser platforms beam energy to spacecraft, producing thrust. Photonic propulsion is still in the experimental stage but offers the potential for high-efficiency propulsion. Aerobraking. Aerobraking involves using a planet's atmosphere to slow down a spacecraft and alter its trajectory. By dipping into the atmosphere and allowing drag to reduce velocity, a spacecraft can achieve orbital changes without the need for propellant. Gravitational assist. Gravitational assist, also known as gravity slingshot, utilizes the gravitational pull of planets or other celestial bodies to alter a spacecraft's trajectory and increase its velocity. This technique is often used to enhance a spacecraft's speed and change its orbital path without the consumption of additional propellant. Spacecraft propulsion systems are selected based on mission requirements, payload mass, destination, and available technologies. Advances in propulsion technology continue to shape the possibilities for future space exploration, enabling missions to distant planets, moons, and even interstellar travel. Each propulsion method has its advantages and limitations, and engineers carefully consider these factors to design spacecraft capable of achieving their specific mission objectives.